Hello, I'm Gentry. I'm a grad student here at UC Santa Cruz, and today I'm going to be talking to you about supernova feedback models. In particular, what happens when you take into account that supernovae are going to be clustered both in space and time. This is work that we submitted back in June, and it's already on the archive, that I did with Mark Krumholtz, Avishai Deckel, and Piero Medal. Some of the stuff, most of this is going to be similar to what was in that paper, but we've been working on it throughout the summer, so there's going to be a bit of things that are different. So we need supernova feedback models. We can't just inject 10 to the 51 ergs into every simulation, because there's a thermal energy in a supernova remnant. It's going to be in a hot bubble, which is going to be separated from where all of the mass that does the cooling. So if you have low resolution, your thermal energy gets mixed with the mass, and you cool everything too fast. So it's usually better to talk about momentum-driven models for low-resolution simulations. Throughout the simulation, the supernova remnant continues to cool, so the energy is continuing to decrease, but the momentum pretty much asymptotes and is flat. This happens on a timescale that's relatively short. So for these single supernova models, it's really easy to separate out the evolution that happens in the bubble from the broader galactic evolution. So that's good. It means we can clearly separate out our supernova model from what's happening in the rest of the galaxy. For these simple single supernova simulations, we have a pretty good idea of what's going on. We know that in this convenient set of units, the momentum that we get out is roughly 3,000. Some authors also include a density dependence in there. But usually these models all assume that you have one supernova going off that's not interacting with other supernovae, which in many systems ends up being an assumption that fails. So for example, this is the centralmost cluster inside of 30 Doradus in the LMC. There's over 70 O stars that are all located within the central 5 parsecs of this cluster. So when these O stars start exploding, it's going to be a bad assumption that they're exploding all isolated and independent for each other. The first supernova is going to explode, and then all of the others are going to be occurring inside of the bubble that results. So we wanted to test what the effect of this was. Is this clustering going to increase, decrease the momentum? How does that affect our models? So we approach this using simulations. I'll talk about the details of the simulations in a second. I just want to give you kind of a picture in your mind of what's going on. So one supernova went off, and a second one goes off, and finally the third supernova goes off for this cluster, and then eventually it's going to merge into the ISM. So we wrote our own code. It's a 1D simulation which uses a Hydro solver written by Paul Duffel over at Berkeley. It uses optically thin cooling that's metallicity dependent, assumes ionization equilibrium. And one of the most important things is we have a realistic model of the supernova delay time distribution. Given a cluster mass, we draw from an IMF until we reach that cluster mass. And for those stars, we can use realistic stellar lifetimes and then realistic supernova ejecta models for both the mass and the metallicity. So for example here, the black tick marks are showing when the supernova are occurring. So roughly, the supernovae start 3 megayears after the cluster forms and continue until 30 megayears after the cluster forms. I showed you a video where there is a 3 supernova simulation. We can do this for 1 supernova. We can do this up to 1,000 supernovae, or anything in between. So we went through and did a systematic parameter study to try to quantify how the number of supernovae affects the amount of momentum that you get out of the system. So in my paper, we also study the metallicity and density dependence, but I'm not going to talk about that today. I'll only be talking about these fiducial metallicities and densities. So the The scatter points are the values from our simulations, the final momentum that it reaches, or momentum per supernova. The line is a Bayesian model that we trained to the data, both of which are included in our paper. The first thing to check is that for a single supernova, we do manage to reproduce the standard value about 3,000 for the momentum per supernova. The surprising thing has been that for like 10 or 100 supernovae, we're getting 10 times the amount of momentum per supernova that we would have expected with one of the previous models. So this was very surprising. And so this means for certain clusters, you can get significantly more momentum than we previously expected. And for an average cluster in a galaxy, you expect roughly 6 supernovae. So even over a galactic-wide scale, this has significant implications for the overall momentum budget. We think we understand qualitatively what's going on, and we think that qualitatively this makes sense. For the first couple of supernovae, the first one's going to go off, and then the second one is going to occur in a lower density bubble. So you would expect that would increase the momentum. On the large bubble side, it starts to behave more like a super bubble. If you go through kind of a Castor and Weaver type of model, you would expect that it would have roughly this momentum dependence, or the dependence with the number of supernovae. So we think that qualitatively it seems to make sense. But this is a simplified model. We're still assuming that this is completely decoupled from everything else that's going on in the rest of the galaxy. Similarly, the people that had the previous isolated supernova models were also simplified. So in reality, it's probably somewhere in between. Some of the reasons why we think that this boost could potentially be lowered by more physical effects. One of them is if you have a multi-phase or turbulent ISM. Some initial work done by Cheng-Gu Kim and Eve Ostreicher seems like that might decrease the momentum boost. If you saw our paper, we initially thought this was due to resolution, but after seeing some more recent simulations, we think this is physical. So it could be because of the ISM. It could be because your super bubble is just going to get sheared out by the disk, by a disk rotation. So it could take it from like the blue point down to the red point. If you take into account a galactic potential, maybe that would decrease it even further. And the same for disk breakout. Eventually, your super bubble is no longer going to be very spherically symmetric. So these last three were all just kind of back of the envelope estimates of what could happen if we start to take into account galactic effects in these models. We can't directly address these in our simplified 1D simulations, but we think it's an important thing to follow up later. So to summarize, let's circle back to that case study of R136. So if there's, it has order 100 supernovae, so you would expect the momentum to be boosted up by a factor of roughly 10 for the amount of momentum that you're going to be getting out of the system. So this is significantly more than what you would have previously expected. But the bubble would take around 150 megayears to expand about a kiloparsec before it finally gets to that momentum. The LMC is only about 4 kiloparsecs, so it's probably a very bad assumption that this is completely independent of the details of what's going on in the LMC. So we think that clustered supernovae could have a significant impact on the momentum budget, but there remain significant uncertainties of how these bubble models should interact with the host galaxy that they're in. This is something that we hope to address in the future, but for now, just be aware that there are significant uncertainties with momentum-driven models of supernova feedback. Thanks.
Questions?
Hi, this is really great work.
One question about the uncertainties that you mentioned at the end. If you were to include a model for the radiation pressure from young stars, which is, there are a lot more models now that are including that in cosmological simulations, that also, before the supernovae go off, they lower the density around the region. Could that also decrease the effect significantly?
So inside of our paper, we make some estimates about what an H2 bubble would cause. Mm-hmm. It doesn't seem to have a significant effect within the uncertainties of our model. But we're not including direct radiation pressure. We're just including the effects of radiation from young stars, of ionization from the young stars. So the radiation pressure would be good to check.
Did you decrease the density?
It depends. It depends on the number of supernovae, the number of density. Oh, it depends on the number of O stars and the density. In some cases, I forget how large it decreases it. In some cases, it's more significant. In some cases, it doesn't affect it at all.
I just want to add, Eric, that given all these uncertainties, if you want to be very cautious, you say the answer is not known, but we did have some speculations, analytic estimates, which tell us maybe the boost is not by a factor of 10, but it's probably a factor of few. So this is to be taken seriously. There is a boost in multi-supernovae in clusters that should be considered.
Other questions? Oh.
Are you including binary stars in your models for the delay time distributions?
No, so right now, we're just assuming that everything is isolated. We have a few tests to see what would happen if we added like a 1A delay time distribution in there. It doesn't seem to affect the answer significantly. But that's pretty back of the envelope.
Any other questions for Eric? Okay, let's thank Eric again. We have a break. Let's return.